Hello everyone, and welcome. Today we're tackling a fascinating problem that connects everyday objects to the fundamental building blocks of matter. Calculating the total charge of all the electrons in a simple copper penny. Understanding this helps us appreciate the sheer scale of electric charge present, even in seemingly neutral objects. First, let's visualize. Imagine our copper penny. Inside, it's made of countless copper atoms. Each copper atom, identified by its atomic number, contains a specific number of electrons. It's these tiny, negatively charged particles whose total charge we want to find. Now for our key variables and constants. We're given the mass of the penny, m, which is 3 grams. The atomic number of copper, Z, is 29. This tells us that each copper atom has 29 protons, and in a neutral atom, 29 electrons. We'll need the molar mass of copper, m, which is approximately 63.546 grams per mole. You can find this on the periodic table. Avogadro's number, Na, is 6.022 times 10 to the 23 atoms per mole. This is our bridge from moles to individual atoms. And finally, the charge of a single electron, E, is minus 1.602 times 10 to the 19th coulombs. Next, the relevant equations. We'll use a sequence of steps. 1. To find the number of moles of copper in the penny, N is equal to m divided by the total mass of copper. M is mass divided by molar mass. 2. To find the total number of copper atoms, number of atoms equals N times Na, moles times Avogadro's number. 3. To find the total number of electrons, number of electrons is equal to number of atoms times Z, total atoms times electrons per atom. 4. And finally, to find the total charge equals number of electrons times E, total electrons times the charge of one electron. Let's plug in the numbers and calculate step by step. 1. Moles of copper, 3 grams divided by 63.546 grams per mole, gives us approximately 0.0472 moles. 2. Number of copper atoms, 0.0472 moles, multiplied by 6.022 times 10 to the 23 atoms per mole, equals roughly 2.843 times 10 to the 22 atoms. 3. Total number of electrons, 2.843 times 10 to the 22 atoms, multiplied by 29 electrons per atom, gives us about 8.245 times 10 to the 23 electrons. 4. Total charge, 8.245 times 10 to the 23 electrons, multiplied by minus 1.602 times 10 to the 19th coulombs per electron, results in a total charge of approximately minus 1.321 times 10 to the 5th coulombs. That's minus 132,100 coulombs. Let's quickly check our answer. The units cancelled correctly, leaving us with coulombs. The magnitude is enormous, which makes sense. Even in a small object, there are an incredibly vast number of atoms, and thus an even larger number of electrons. This large negative number tells us the total charge if we could somehow isolate only the electrons. In conclusion, the total charge of all electrons in a 3-gram copper penny is approximately minus 1.321 times 10 to the 5th coulombs. This problem beautifully illustrates the link between macroscopic properties, like mass, and the microscopic world of atoms and subatomic particles. This approach can be applied to find the total charge of electrons in any substance, simply by knowing its mass, atomic number, and molar mass. A key insight here is that while the total charge of electrons is massive, everyday objects, like our penny, are electrically neutral overall because they contain an equal number of positively charged protons, perfectly balancing out this huge negative charge from the electrons. It highlights that charge at its most fundamental level is quantized, meaning it comes in discrete packets, the charge of a single electron. So, the key takeaway is that by knowing an object's mass and its atomic composition, we can systematically determine the immense quantity of electrons it contains, and thus their total collective charge. This problem reinforces fundamental concepts like Avogadro's number, molar mass, atomic structure, and the quantization of charge, all interconnected ideas in physics and chemistry. Thank you for joining this session. If you found this explanation helpful, please consider liking this video, subscribing to the channel for more physics and math insights, and sharing it with anyone who might benefit. Feel free to leave any questions or comments below. And if you have a specific problem you'd like to see solved in a future video, consider donating to the channel. Each month, we'll select a few donor-requested problems to tackle.